To properly support navigation meshes, we need to make sure that they are all convex meshes. Now, convex meshes means that they have a shape similar to this, or to this, or even triangles. Triangles are always convex. A convex polygon, like this, allows us to move from any position on that polygon to any other position in a straight line without intersecting an edge, which is really important when it comes to our navigation meshes because we don't want our AI moving through walls. A concave polygon would look something like this, where it sort of has this inward edge here, or potentially a shape that looks like this, where it has an inward edge there, right? These shapes would not work for navigation meshes, because if an AI stands from this position and wants to move to the position over here, it would move right through these walls. So what we need to do is go through a process called convex decomposition. Convex decomposition is the process from going from a concave polygon or set of polygons and converting them into convex polygons that represent the same shape. As an example, if we're to run this polygon, which is currently concave, through a convex decomposition logic, we might end up with something that looks like that, where now it is represented by two shapes, both of which are convex. Or we could also end up with a shape that looks like that, right? This turned it into a series of, 5 different triangles, but it's still together. They all represent the exact same shape. So the first thing that we need to do is, if we're generating polygons based on the sizes and shapes of our level, we don't know if those polygons are going to be all concave. So we need to go through a process of convex decomposition. Most convex decomposition algorithms go through the first initial process called triangulation. Triangulation is the process of taking a polygon and converting it into a series of triangles. And you can do this even on convex polygons like this. This polygon could be triangulated by creating edges between the various points on them. So I could triangulate this polygon by connecting some of these edges like this, connecting some of the vertices like this, and now I have 3 triangles that represent the same walkable space. There's a handful of different convex decomposition algorithms, and there's also a handful of different triangulation algorithms. The one I'd like to talk about right now is something called an ear cut algorithm. The ear cut triangulation algorithm is a relatively straightforward algorithm that essentially walks through all of the points on a polygon and tries to cut off, they're called ears, tries to cut off various points within them. I'll show you how the process works. Imagine we have a polygon that looks like this, right? The first thing that an ear cut algorithm would do is select a vertice that on the outside edge, right? So the first thing it would do is select a vertice. So let's say that it selected this vertice here. What it would do is it would look at the next 2 vertices and determine whether or not it could cut that set of 3 into its own triangle. Right? In this case, the answer is yes. So it would add a new edge. It would add a new edge here, and then this piece would be cut off into its own triangle. Then it would explore the next vertice. Now we're going to explore this vertice. And it would ask, is this vertice and these 2 adjacent vertices, can this be cut off into its own triangle? In this case, the answer is yes. And so now it cuts again. Now we end up with just 3 remaining vertices in the original polygon. So we've successfully done an ear cut algorithm on this and generated 3 different triangles. Let's take another look at when the edges potentially could not generate a triangle. Let's say that first we explore this vertice here. Well, it would look at the adjacent 2, 1, 2, and it would determine if it could cut off that these three into its own triangle? The answer in this case is no, because cutting off this one here would actually result in a triangle that is not representing space within the edge like this. A check like this can be done like relatively quickly just based on the angles between the adjacent vertices. So in this case, the Earcut algorithm would essentially rule out that it can't cut based on that vertice, and it would move on to the next vertice. So it would move down to this one. And then it would say, okay, let's look at the adjacent three. Can I cut a triangle based on these three? The answer here is yes. So I'm going to make a cut. And then it would move to this vertice and say, can I cut based on the adjacent three? And the answer is yes. So it would make another cut here, right? Notice how this actually produced different polygons just based on which vertice I started with. Now, this is totally fine. Both of these sets of triangles represent the exact same space.